In this video, we're going to do one thing and one thing only, and that is find a basis for the null space of a particular matrix. We are going to work through one example where we explicitly write this down. So our matrix here is a 3 by 4 matrix. When you find the basis for the null space, the first thing that you're going to do is to put that matrix into reduced row echelon form. Now, I have all of the steps written down in advance here, and if you need to pause the video to catch up, feel free to do so. But there's a sequence of row operations that takes you all the way down to the reduced row echelon form of this matrix. And then we're going to be analyzing that reduced row echelon form really closely. So we're going to be looking at this matrix with 1, 0, 0, 2, 0, 0, 0, 1, 0, and 3, 1, 0. And the question that we're going to be asking ourselves is, which of these vectors are independent vectors, and which of these vectors are linear combinations of the vectors that came before them? When I look at this matrix, I see that there are two vectors which are independent vectors. These are the ones that I've highlighted in pink, 1, 0, 0, and 0, 1, 0. These look like standard unit basis vectors in this matrix. And then I also have two other vectors, the ones that I've highlighted in green. These are the two vectors that can be written as linear combinations of the previous two vectors. One thing that's important to keep in mind as we do this null space problem is what the null space is. The null space is the vector space of the vectors x that solve the equation ax equals 0. So along with this matrix that we produced, we can think about the system of equations that goes along with it as well. So what we have here are the pivot columns, and then we have the other two columns that are linear combinations of what comes before. And we can see that by just looking at the matrix, but we can also see that from the system of equations. So for example, when I look at this and I look at the vector 1, 0, 0, that's the first column, and I look at the second column, that's 2, 0, 0. It's obvious in this reduced row echelon form that this second one here is 2 times 1, 0, 0. It's a multiple of the first column vector. And I can also do something similar for the last one. So if I look at the vector 3, 1, 0, this is the fourth column from my matrix. I can write this in terms of the previous vectors as well. This is equal to 3 scalar multiplied times 1, 0, 0, plus 1 scalar multiplied times 0, 1, 0. This gives me the combination 3, 1, 0. So what this is actually 3 times column number 1 plus 1 times column number 2. And this is giving me column number 4. So these linear relations, that 2 times column 1 is equal to column 2, and then 3 times column 1 plus column 2 giving me column 4, show me that the two columns that I highlighted in green are really linear combinations of the two columns that I highlighted in pink. We can also write this as a system of equations like this. This matrix above can be written as x1 plus 2x2 plus 3x4 equals 0. This is the equation that goes along with the first row here. And x3 plus x4 is equal to 0, and then the last row, which is all zeros, tells me that 0 is equal to 0. I wanted to remind you all that we're solving the equation ax equals 0. This means that this matrix, that's a 3 by 4 matrix, goes along with the homogeneous system of equations, which means we've set all the equations equal to 0. And then we've put in x1, x2, x3, and x4. We need all of these variables to describe this system of equations. So when you look at it this way in terms of a system of equations, you can also see that you've got two free variables and then you've got two dependent variables. You could set x2 and x4 to be anything. These can be any real number. But then once you've said what x4 is, it completely determines what x3 is because of this equation. And likewise, once you've figured out what x2 and x4 are, that completely determines what x1 is from this equation. So you have two free variables and then two variables which are not free. So it may be helpful for you to think about parameterizing the solutions to this system of equations. When we do that, we write down something that looks like this. So we have our free variables, x4, and we have x2, and we parameterize the system of equations by naming our free variables. So we would name x4, say t, and we would name x2 s. These are the ones that could be set to be any real number. And then you have little equations for x1 and x3. x3 has to be equal to minus t, and x1 has to be minus 2s minus 3t based on these exact equations right here. Let's now take these solutions and write them in vector form. Okay, I'm going to make space here so we can keep this all on the same page. In vector form, the solutions to this system of equations are vectors that look like x given by minus 2s minus 3t, that's our x1, s minus t, that's our x2 and our x3 and our x4 that we got from this system of equations over here. Now I'm going to split these up. I want to pull out an s and I want to pull out a t like it's a scalar. S is multiplied times minus 2, 1, 0, 0. And t is multiplied to the vector minus 3, 0, minus 1, 1. This is a way of writing this vector as a linear combination, where s and t are the scalars. And now these two vectors that show up here, minus 2, 1, 0, and minus 3, 0, minus 1, 1, these two vectors form the basis for the null space. So my basis for the null space of the matrix A that I started out with. It has two vectors in it, and it's these two, minus 2, 1, 0, 0, and minus 3, 0, minus 1, 1. Because anything that solves the equation ax equals 0 is of the form scalar times minus 2, 1, 0, 0 plus scalar times minus 3, 0, minus 1, 1. That's what it means for these two vectors to be a basis for the space of solutions to ax equals 0. And that's the definition of the null space. It's the set of solutions to ax equals 0. Now, we can arrive at the same answer, these two vectors, without having to write down the system of equations like what we did here. But I wanted to make it clear that these solve ax equals 0. You can actually get at the answer directly from the matrix and the vectors at this step up here. So let's go over that now and get to the same answer in that way. So let's think more about those linear dependencies that we saw in the matrix. Our matrix that we ended up with after we row reduced everything was this one. We have 1, 0, 0, 2, 0, 0, 0, 1, 0, and 3, 1, 0. Okay. And as we observed before, there's some linear dependencies that are easy to observe because the form of this matrix is so simple. Let's look at the first linear dependency. This is the one that says that 2 times column 1 is equal to column 2. That's because 2 times 1, 0, 0 is equal to 2, 0, 0, which is right what I see here in the matrix. All right, now I'm going to rewrite this equation just a little bit, and I'm going to put everything on the same side of 0. So the 0 vector, in other words, is equal to minus 2 column 1 plus 1 column 2. And you know, column 3 and column 4 don't show up in this equation, but I could put them in there. There's also a plus 0 column 3 plus 0 column 4. So if I take a look at this linear combination, I'm going to take the coefficients out of it. So I want to take the minus 2, I want to take the 1, the 0, and the 0. And let me put those coefficients into a vector. Minus 2, 1, 0, 0. Hey, we've seen this vector before. That's this vector right here. This is one of the basis vectors of the null space. The linear dependency of the matrix can be explicitly described as a relationship between the column vectors. I rewrite that relation so that I have 0 equals combination of the columns, and then I encode that combination right here. This gives me one of the basis vectors of the null space. Let's do it again, and we're going to see this vector show up. Okay, the linear dependency for the next one deals with column 4. And what we saw for column 4 was that we needed to take 3 times column 1 plus 1 times column 2. Column 3. And that gave us column 4. So let me put everything on the same side of the equals now. The 0 vector can be written as -3, column 1, minus or plus 0 times column 2, which didn't factor in there at all, -1, column 3, plus column 4. That's the combination that gives me the 0 vector. Now let me do the same thing. Let me take the coefficients, -3, 0, -1, and there's a 1 here. So let me write in that 1 times column 4. And let me transcribe that into a vector, -3, 0, -1, 1. And that's this vector right here, the other basis vector. So I did the same thing. I looked in my matrix at my 2 dependent columns. Those are the ones that I had previously highlighted in green. It was column 2 and column 4. For each of these dependent column vectors, I have a dependency relation that I can write down that says, how does this depend on the other columns? I use that to write a linear combination that gives me the 0 vector. And that I transcribe into a vector. That's what I did here for column 4. Column 4 can be written in terms of the other columns. So I solve for 0. I put the coefficients into this vector, and that gives me the second basis vector. For every dependent column, I get a basis vector of the null space. So you see here, there are 2 different ways to arrive at the same answer. I can go out of the system of equations and parameterize the solution, or I can use the dependency relations of the matrix. And to recap, when I started this process and I had my original matrix, the very first thing that I had to do was to put the matrix into reduced row echelon form. So this is how you find a basis for the null space of A.